Is it possible for light to travel backward through time, defying our everyday experiences? Imagine a world where a ray of light, instead of moving forward, travels back to its source, like a movie played in reverse. This intriguing concept, known as retrocausality, challenges our fundamental understanding of time and the universe's workings. It suggests that the future might influence the past, a mind-boggling idea that has captivated scientists and philosophers for decades. Our everyday experience tells us that time flows in one direction, from the past through the present and into the future. We see a glass shatter after it falls, not before. We remember yesterday, not tomorrow. This intuitive understanding of cause and effect, of time's unwavering arrow, is deeply ingrained in our perception of reality. Yet at the heart of modern physics, in the realm of quantum mechanics, the rules of the game appear different. The subatomic world, it seems, dances to a different tune, where particles can exist in multiple states at once, where uncertainty reigns supreme. And it is in this strange and wonderful world that we find the seeds of retrocausality, of the possibility that time, at its most fundamental level, might not be the straightforward, unidirectional arrow we perceive it to be. One of the most compelling pieces of evidence hinting at the possibility of retrocausality comes from the strange phenomenon of quantum entanglement. Imagine two particles born from a single event, linked in such a way that they share a destiny, no matter how far apart they may be. Change the state of one particle, and instantaneously, the other particle, even if it's light years away, will mirror that change. This spooky action at a distance, as Einstein famously called it, has been experimentally verified time and again. But how can two particles be so intimately connected, their fates intertwined even across vast cosmic distances? One possible explanation, and it is here that retrocausality enters the picture, is that the particles are not communicating instantaneously across space, but rather, they are influencing each other through time. Imagine, if you will, that the future state of one particle can influence the past state of its entangled partner. This would mean that information can flow not just from the past to the future, but also from the future to the past. It's a dizzying concept, one that challenges our very notion of causality. But it's a possibility that arises when we try to make sense of the deeply puzzling, yet undeniably real phenomenon of quantum entanglement. The idea of information traveling backward in time might seem like something out of science fiction, but it finds support in certain interpretations of quantum mechanics. One such interpretation, known as the transactional interpretation, suggests that quantum events are not isolated incidents, but rather, they involve a kind of handshake across time. Imagine you send a text message to a friend. In the transactional interpretation, sending the text is like sending a proposal into the future. Your friend receiving the text is like sending a confirmation back to the past. The actual event of the text message being sent and received only happens when this transaction across time is complete. Applying this to the realm of light and particles, it suggests that a photon, the fundamental particle of light, might not just be traveling through space, but also negotiating its path with its future self. This could mean that the future state of a photon influences its past behavior, hinting at the possibility of light, in a sense, traveling backward in time. The concept of retrocausality isn't limited to the realm of theoretical physics. Experiments have been devised to test the limits of causality, to see if we can catch glimpses of the future influencing the present. One such landmark experiment is the delayed choice quantum eraser experiment, which builds on the famous double-slit experiment. In the double-slit experiment, photons are fired at a barrier with two slits. Instead of behaving like tiny marbles, passing through one slit or the other, the photons act like waves, passing through both slits simultaneously. This wave-particle duality is a cornerstone of quantum mechanics. But here's where it gets even stranger. If we try to observe which slit a photon goes through, its wave-like behavior collapses, and it acts like a particle going through only one slit. The act of observation seems to force the photon to choose a path. Now imagine delaying the choice of which slit to observe until the photon has already passed through the slits. This is the essence of the delayed choice experiment, named after physicist John Wheeler. Astonishingly, even when the choice is made after the photon should have already decided its path. the photon still behaves as if it knows what choice will be made in the future. This experiment suggests that the future observation is somehow influencing the photon's past behavior. It's as if the photon, already on its journey, receives a message from the future, telling it how to behave. This challenges our intuitive notion of time flowing in one direction, hinting at the possibility that the future can indeed influence the past. It's important to remember that these experiments are pushing the boundaries of our understanding. They don't provide definitive proof of retrocausality, but they offer tantalizing clues, suggesting that the universe might be even more bizarre and wondrous than we ever imagined. The implications of retrocausality, if proven true, are profound. It would mean rewriting our understanding of the universe's fundamental laws, shaking the very foundations of physics as we know it. One of the most immediate implications is the nature of causality itself. If the future can indeed influence the past, then our straightforward understanding of cause and effect, the bedrock of scientific inquiry, would need to be reevaluated. Could an effect precede its cause? Could the future be shaping the present as much as the past? These are not just philosophical questions. They cut to the heart of how we understand the universe and our place within it. If the future can influence the past, then the universe is not a static, predetermined machine, but rather a dynamic, interconnected web where past, present, and future are inextricably intertwined. Imagine a world where ripples in the fabric of space-time, gravitational waves, could carry information not just from the past, but also from the future. This is just one of the mind-boggling possibilities that arise if we entertain the notion of retrocausality. If the future can indeed influence the past, then perhaps black holes, those cosmic monsters where gravity is so strong that not even light can escape, could hold secrets not just of the past, but also of the future. Perhaps the event horizon, the point of no return around a black hole, is not just a boundary in space, but also a gateway through time. These are, of course, speculative ideas, but they highlight the profound implications of retrocausality. If the future can whisper to the past, then our universe is a far stranger and more wondrous place than we ever imagined. Section 8. The quantum eraser, erasing the past. Another intriguing experiment that hints at the possibility of retrocausality is the quantum eraser experiment. In this experiment, the choice of whether or not to observe the path of a photon is not just delayed, but it can be seemingly erased after the fact. Imagine, once again, the double-slit experiment. This time, however, we entangle a second photon with the first, and this second photon carries information about which slit the first photon went through. If we measure this second photon in a specific way, we can erase the information about which slit the first photon went through. Astonishingly, even though we've erased the information about the photon's path, the photon still behaves as if it knows whether or not that information was ever known. If we erase the information, the photon acts like a wave, passing through both slits. If we didn't erase the information, the photon acts like a particle going through only one slit. The quantum eraser experiment, like the delayed choice experiment, pushes the boundaries of our understanding of time and causality. It suggests that the act of observation, of gaining knowledge, can have a retroactive effect on the past behavior of a particle. It's as if the photon, having already journeyed through the slits, can somehow rewrite its history based on whether or not its path was ever observed. These experiments, while not definitive proof of retrocausality, open up a Pandora's box of possibilities. They suggest that the universe might be far more interconnected, far more mysterious than our classical intuition tells us. If the future can indeed influence the past, if information can flow backward through time, then the universe is not a collection of isolated events, but rather a grand, interconnected web, where past, present, and future are woven together in ways we are only beginning to glimpse. The implications of retrocausality extend far beyond the realm of physics. If the future can indeed influence the past, then our understanding of free will, of the choices we make, takes on a whole new dimension. If our actions in the present can be influenced by events in the future, then is free will an illusion? Are we merely puppets? Are strings being pulled by the inexorable hand of destiny? These are profound questions questions that philosophers have grappled with for centuries, and questions that retrocausality brings to the forefront of scientific inquiry. Of course, there's a difference between influence and predetermination. Even if the future can whisper to the past, it doesn't necessarily mean that our fates are sealed. Perhaps the future influences the present not by dictating our choices, but by shaping the landscape of possibilities within which we make those choices. The concept of retrocausality, while still speculative, has the potential to revolutionize our understanding of the universe. It challenges our deeply held intuitions about time, about cause and effect, about the very nature of reality itself. If the future can indeed influence the past, then the universe is not a static, clockwork mechanism, but rather a dynamic, ever-evolving dance where past, present, and future are inextricably intertwined. This is a universe of possibilities, a universe where the arrow of time might not be an arrow at all, but rather a Mobius strip, twisting and turning back on itself. It's a universe that sparks the imagination, that invites us to question our assumptions, to explore the boundaries of what we think we know. It's a universe that reminds us that the more we learn, the more we realize how much we don't know, and that the greatest discoveries often lie hidden in the most unexpected places. So, can light travel backward through time? The answer, as with many things in the quantum realm, is not a simple yes or no. The experiments we've explored, while suggestive, don't offer definitive proof. But they do open up a world of possibilities. A world where the future might not be so far removed from the past, where the arrow of time might not be so straight after all. The study of retrocausality is still in its infancy, but it holds the potential to revolutionize our understanding of the universe. It challenges us to rethink our assumptions, to embrace the unknown, to explore the boundaries of what we thought was possible. And who knows what wonders we might find, what secrets the universe might reveal if we dare to follow the light, even if it leads us backward in time. If light can travel backward through time, what does this mean for our understanding of cause and effect? And how might this discovery change the future of physics? The answers to these questions, like the universe itself, are full of mystery and wonder, waiting to be explored.